Hello everyone, welcome back. In this week's videos, we're going to talk about data sonification. So far in these series of tutorials, we've explored capturing data, turning data into visuals. For this portion of the course, we're going to explore the idea of taking data and turning it into sound. And that's a pretty open-ended field. We could spend several weeks on this concept alone. But for today, we're going to focus on two kind of strategies for sonifying data. One is going to be looking at the data and then mapping it to some raw sound generators, things like oscillators, and mapping the properties of the sound directly to data and to see what kind of results we can get from that. Using that technique, we're going to get sort of like a lot more noisy, kind of glitchy results. And then the second approach we're going to explore today in the second half of the video is going to be a little bit more musical. So trying to map the data to actual musical notes and then getting an instrument to play those back in an attempt to create something a little bit more melodic. And of course, the data could be anything. For today's example, we're going to start off from last week's little binary sort of Ryoji Ikeda inspired test pattern ripoff project. And we're going to start with this one, and we're going to just add some sound to it for the first example. And then we'll use a different data set for our second example this week. All right. So this is the example we ended on last week. So the first thing I'm going to do is I'm going to just remix this into something new. And we are going to call this um, let's call it OSC for oscillators. Sonify. Okay. That's good enough for now. Okay. So I'm going to remix this into a new project here. Okay. And the visuals are a little bit intense. So the other thing I'm going to do right away is just going to sort of maybe comment out here for now the drawing of the actual lines. Okay? Just so we don't get totally crazy having that flashing in our face the whole time, while I talk a little bit about what we're going to do for the sound aspect. Everything else we're going to leave the same. If you need a refresher as to what that program is, just watch the previous video that I recorded. But basically what it does is it loads a data file here. In this case, we're using an MP3 file. And using the glitch library, accesses the file's raw bytes using the load bytes function. And we do a little bit of kind of slicing things up here by randomly taking chunks of bytes and copying them over other chunks. This is just for fun. And I'm going to leave that in there. Why not? I mean, it doesn't really matter. And then over here, sorry, over there, the other thing we did last week is we took those bytes and then turned them into an array of zeros and ones. So the binary representation for those bytes. And decided to make a little visualization based on that. So turning the zeros and ones into black or white rectangles and then going through the array over time to create an animation. So for today's example, we're going to be talking about adding a layer of sound to this. So this is how we're representing the data visually, right? So we are turning these into these rectangles and boxes that I can't see now because I've commented out. We could also think about, just like in Ryoji Ikeda's piece, adding a layer of audio to this. Now, obviously, what we're going to do today is nowhere near the level of sonic mastery of Mr. Ikeda, but it's going to demonstrate the idea, and then you can explore that on your own and see what you can do with the concept. So in order to get some sounds, we're going to need to rely on a sound library. Now, P5.js does come with a sound library called p5.sound, but I'm not going to use it today because, I mean, it kind of works, but I've had some bad luck in the past with it. It hasn't been super reliable, at least for me. And whenever I'm doing sound in the browser, I tend to prefer using a library called Tone.js. Okay? So Tone.js is a great library that kind of provides all of the basic for doing generative sound inside the browser. It's going to allow you to create oscillators, which are just raw sonic waveforms. all the basic building blocks you would have for creating something like a synthesizer, for example, things like envelopes and noise and mixers. It also allows you to load in some samples. We're going to explore that in the second example today, where you can load samples, not just create sounds from scratch. It also has some effects, things like reverberation. You can apply modulation to your sound using LFOs or low frequency oscillators. So it's a really fun kind of playground for creating audio applications. So we're going to use this library, and the oh, there it is over here. And there's a couple tricky things I want to mention about this, because the one downside of Tone.js is that it is not as easy to get into as p5.sound. The reason I say that is because p5.sound has great documentation on the p5.js website, kind of following in the same philosophy of p5.js. It's very easy to get into for beginners. So coming from the world of p5, jumping into Tone.js may feel a little bit intimidating. For example, all the examples are, if I click on an example here, let's say the oscillator example, right? So just playing an oscillator, it doesn't have any source code with it, or it seems like it. That's because they're all designed for just kind of pure HTML and JavaScript. You can always look at them by looking at view page source, right? And then you'll be able to see the actual JavaScript code in here that allows you to create these objects. So it's not a huge hurdle, but if you're not super comfortable with JavaScript and you're kind of more familiar with P5 and the relative ease of that environment, jumping into Tone.js can sometimes be a little bit intimidating. But I'm going to walk you through at least the very basics today, so that you can start to explore ideas around sonification. The other thing that can be a bit of a roadblock is there are no clear instructions on how to install this library on the website if you're not within the Node.js environment. Now, it is available on most of the content delivery links that we've been using to install libraries. I remember from a previous version of the library that using unpackage was the preferred version of accessing it. So I'll put a link to that, the current version anyway, as of creating this video, into the video description, so that if you want to import the library, you can use that link, or you can remix this sketch and then start over. So the first step we need to do is import the library. So I'm going to add this link here, just like CDN.js here. Unpackage is another content delivery network that takes Node packages and then provides them through the web for your scripts. So this is importing the current version of Tone.js and just adding it to our scripts. And I guess it doesn't matter what order I put it in, but I'll put it there. So that is the first step, and it's not obvious how to do this, at least from this current documentation. All right. So having done this, let's just jump into it and create our first sound. So we're going to call, for this example, we're going to create an oscillator. So an oscillator is an object that will generate a waveform that's going to produce audio. Now, those are raw waveforms, things like sine waves, triangle waves, square waves, and we're going to be able to control that oscillator's amplitude, that's going to be its volume, and its frequency, that's going to be its pitch. And we'll also be able to apply some effects to it. So I'm going to declare here a global variable called OSC, that's going to be our oscillator. And somewhere at the end of draw here, we're going to set up the oscillator. So we are going to create it using this line of code here. We're going to say new tone.oscillator. And when we create the oscillator, we are going to specify two things. First is going to be the frequency that oscillator is going to be playing at. So let's put in 440 hertz to start with. We're going to change that soon with our data. So the data is going to change the pitch of the oscillator, but we're going to give that a starting frequency. 440 hertz, by the way, is equivalent to an A4 note on a piano. And the second parameter is going to be the type of waveform we want to create. Okay, so I'm going to go with a sine wave to start with. And other types are, you have things like triangle or square. All right, so we're going to create this oscillator, and then we are going to connect it to the output of the library, the sound output. Now, Tone.js has this metaphor for it called the destination. So whenever you see to destination in the Tone.js documentation, it means that you're connecting something to essentially think of it as the speakers or the headphones, right? The audio output of your program. So Tone.js is built around this modular kind of framework where all the individual sound objects by default are just not connected to anything. When you create an oscillator, in order to hear its sounds, you have to plug it into something. And that way you can create a signal chain, right? You can have oscillators connected to effects and then effects connected to your destination or your sound output. And the destination in Tone.js lingo just basically mean the final sound output. We'll see in a bit an example where we're going to connect this oscillator to something else than the destination, because we're going to insert an effect in between the oscillator and the final sound output. Okay, so if I hit refresh here, now we've created our oscillator object. We've connected it to the destination. The last step we have to do is actually start the oscillator to just get it going so it can start to oscillate. And this is a little, I'm going to do it here, and it's worth pointing out that something interesting will happen here we have to consider when we're writing audio applications. So now you can hear a pitch, right? We can hear the pitch. This is the 440 hertz pitch from my oscillator. I'm going to turn it off here by refreshing. Notice that if I open this in a new window and refresh, oh, it still kind of works. Okay. So interesting. I'm not sure why that is, but this is something we have to be a little bit careful with, because when we start sound in JavaScript, we usually want to make sure that the browser has been interacted with beforehand by the user. And if that's not the case, sometimes the sound just won't start. Okay? That's part of some policies that browsers have to prevent websites from just kind of blasting audio at you without you knowing it. If something just opens, and usually you have to interact with it in order for the audio to start. Okay? So we're going to implement that in our code. We're going to create a variable here called ready. And the way we're going to use this is inside mouse pressed. Let's get rid of this key pressed here. We'll say wait for if ready is false, right? So if we're not ready, we're going to start our oscillator and we'll set ready to true. So we're going to wait until we click in the window for the oscillator to start. That's also going to have the benefit that if I hit refresh, the sound's not going to start right away. When you're programming, that can get pretty annoying. So now I'm going to have control over when it starts, and I can stop it by hitting refresh. Worth noting that I have refresh app on changes disabled right now. Okay. So now we have this variable that's going to wait for a mouse press. It's only going to start it once because this Boolean is going to be set to true as soon as we do our first mouse click. We can also use that variable if we wanted to in draw here. We could say if ready, we're going to do this that we are currently doing. So I'm going to format it to indent. Okay, so if ready, we're going to do this, and then else we could display a little prompt. Something like we could display a little prompt to the user to click into the window, right? Something like that. Let's do in the center and text align center. This could be whatever, but now the website is prompting us to interact. When I click, this is going to disappear because the ready flag will change its value, right? And we'll either be doing our main program or drawing the text, drawing the prompt. Okay. So we've created an oscillator. We've connected it to the destination, which in other words means takes the oscillator, plug it into your speakers, and we are starting the oscillator on a mouse press. So the next thing we can look at is let's have the pitch of that oscillator vary according to what's happening with our data. Okay? So we know that in this for loop here, this is where we're drawing our rectangles, and I've commented them out for now because I don't want to be staring at them. We'll bring them back in a second. We have this if statement here that's checking our binary array that contains our zeros and ones and decides on whether or not to do a black or a white fill according to the value, okay, the 0 or the 1. So we could say, okay, well, what we could do here is let's also create a count. Okay, so there's any number of ways we could decide to map this data to the sound. This is the fun part of sonification, is we know we have this data, we have a sequence of zeros and ones, and we're going to experiment with ways that we can represent the data sonically. So what is that mapping? Well, that's pretty open-ended. For example, one way we could decide to map it, we just say, let's count the number of zeros that we have, okay? And it's called a zero count. So in a given frame that we're drawing, whenever we decide to set a black fill, let's also go in and increase zero count. Okay? And we'll make sure this starts at 0, not undefined. So this variable now is going to contain the number of zeros we're displaying, okay, in the window. So having that, we can then say, let's change the frequency of our oscillator. Okay? So the oscillator object, let's open up the console here so it's a bit easier to demonstrate. The oscillator object has a bunch of things we can do to it, but the most basic thing we can do is set its frequency. So we have oscillator.frequency here, right? And frequency is not a variable in Tone.js. It's actually also a kind of object called a signal. And this is an important concept from Tone.js. A lot of the values like frequency and amplitude and things like that, they're not actual fixed values. There's something called a signal, which means they could change over time and they could be animated. So if we want to set the value of a signal, we have to use the name of that attribute and then use the value variable. So I'm going to say, for example, if I were to refresh here, click, I could change the pitch of my oscillator by setting it to different frequency values. Or we could like wake up the cats here and go high pitched. Okay. Wow, that's pretty annoying. All right. So what we're going to do for a little experiment is we are going to set the frequency of this oscillator based on the number of zeros we encountered. So we're going to map the number, because if we just use the number by itself, it's not going to be that interesting, right? I have maybe like 50 values across the screen, so I'm going to get a number that's too low for an actual pitch, an actual frequency. So we're going to map a zero count. So what is zero count going to vary within? Well, it's going to be a number between 0 and n, right? Where in this case here, n is the total number of rectangles that I'm drawing. So if all of them were black, if the whole screen was black, right, then we would have zero count would be equal to n. Otherwise, it's going to be equal to 0. So let's map this to a number where if there is almost no black, we're going to go high pitch. And if there's a lot of black, we're going to go low pitch, right? So we're going to have high pitch frequency if there's no black, and a low pitch frequency if there's if the whole screen is black. So let's see what that sounds like. And we'll put the rectangles back in now, just so that we can see the correlation between the visuals and the sound. So here is low pitch, there's no. Interesting. There's a bit of a lag here for some reason. I don't know why that is. Let's try it again. Oh, of course. I'm trying to set the frequency inside the for loop. So that's a bit of a problem. So this is changing the frequency for every square that's being drawn, and that's going to create some strange results. So I want to do that over here. So after yeah, that makes more sense. So after we've drawn all the rectangles, we've counted how many of them have a 0 value. Now I want to set the frequency here. Let's see what that sounds like. So that should be more in sync with the visuals. So kind of a basic idea, but this is something that we can play with. So let's try to add a little bit of interest to this. In addition to changing the frequency, what other data could we get access to from this data set that we could play with to try to affect the sound and make it a little bit more dynamic? So we have access to zeros and ones. I mean, we have the zero count. Theoretically, we could do the opposite of the zero count, right? We could do the one count. We could, for example, create a second oscillator and have that oscillator's frequency controlled by the number of ones, kind of be the opposite of the zero count oscillator. Let's try that, see what that would sound like. So we're going to create a second oscillator, and we are going to make it a sine wave as well. Connect it to our destination, OSC2. And we are going to start the second oscillator. And let's map that oscillator's frequency value. We're going to use zero count again. Now, zero count is between 0 and n. And that means that when there are no zeros, it means we have only ones. Okay, so we don't need to go and create a one count because we either have zeros or ones, right? So the opposite of the zero count is going to be the one count. Okay? So we could imagine, okay, let's figure out, maybe this, when there's a lot of ones, right, this oscillator is going to go even higher pitch, maybe twice, So what I'm doing here, by the way, so 440 is an A4. If I double the frequency, I increase by 1 octave, right? So I go up 1 octave. If I divide by 2 or divide by 4, I end up with 220, 110 hertz. So I'm just varying by octave the boundaries of my sound right now. So let's go between, let's say, I don't know. So the one frequency is going to vary to some other range, and see what that sounds like. So now it's a little bit more dissonant, right? Because we have these two oscillators, and together they're kind of creating this dissonant chord tone because we're not really tuning them with the mapping. It doesn't take into account notes or anything like that. It's just moving the frequencies, but creates a sound that's a little bit harsher and maybe a little bit more in line with the visuals and kind of that feeling we're trying to convey, perhaps. So this is like a lot of experimentation can take place here, trying to come up with stuff that sounds interesting and coming up with different ways that you can map the data to attributes of the sound. If we wanted to have more to play with, then we would have to start thinking about, okay, well, what are some other patterns that we can find in the data that are not just the obvious, what are the individual data elements? For example, we could look for the amount of change that we see in a given screen, right? How often does the squares go from a 0 to a 1, or from a black to a white square, or vice versa? So let's calculate the amount of change. Okay? And that's going to give us one more data point that we can try to map to the sound. So we need a few variables to do that. Basically, we're going to create a counter so that every time we see a change from black to white, we're going to increase that counter by 1. So that's going to be the amount of change. And in order to know if we have a difference, right, if we switch from one to the other, we need a variable to keep track of what the previous value was. So we'll assume we start on black. It's not going to be perfect, but just see what happens. So over here, we're going to have to look at our bit again here. So let's take that and put it into a variable. Let's call it bit, so we don't have to do this part twice. Okay. And here we're going to look for change. So we'll say if bit is not equal to previous. In other words, if the bit we're reading is different from the last thing we stored inside the previous value, we're going to count that as a change. And then we're going to set previous equal to bit. And that means the next time this will update, right, it's going to take bit to be different from the value inside previous. So this little algorithm here will look for changes in the data. So it's going to look for a change from 0 to 1 or a change from 1 to 0. And now we have this new number that we could play with. That's going to vary between 0 and its upper bounds is going to be half of n, right? Because the worst case scenario, if everything changes every other bar, it means that the total number of changes will be half the number of bars that we are drawing. And we could take a look at that number if we wanted to. We can log it to the console, but I know it's going to be a number between 0 and half of n. So what could we map it to? Well, anything really that we can come up with. One thing that we could try to play with is adding some effects to the sound. So we're going to go and create an effect called tremolo. Okay, so tremolo is going to vary the amplitude of the sound, and we want to vary both oscillators together. So it's going to kind of create this vibration effect in the output. So what we're going to do is we are going to first we're going to start and create the tremolo. Okay, so we'll say new Tone.tremolo. So this is one of the effect objects that we have access to. And then we are going to say, okay, tremolo, what are the values that it takes as a parameter? Well, let's take a look at the documentation here. API. So in the effects, we have access to tremolo. Let's take a look at the constructor. So the tremolo wants to see two parameters. One is the frequency of the effect, so the rate of the effect, and then the depth. This is how much it's going to affect the amplitude. So that frequency, it should be a low number. So this is different from the frequency of our pitch here, right? A low frequency oscillator, usually it's going to vary between, let's say, like 1 and like 10 or 20 hertz, something that any faster than that is going to start to go into audio range. Okay? So let's start with 9 hertz as a starting point, like they do in the example, and we're going to put a depth of 1, so it's going to be a very pronounced tremolo. Now we're going to take this tremolo, oops, should be new here, and we are going to connect it to the destination. Okay. Right. Now, if we do this, right, this is not going to have any effect. It's hard to tell here, but all we can hear is our oscillators. That's because our oscillators are going straight to the destination, and so is our tremolo, but there's nothing going into the tremolo, so it doesn't have anything to process, anything to give its effects to. So what we're going to do here is, instead of connecting the oscillators to the destination, we're going to connect them both to the tremolo module, or the tremolo node in our signal chain that we're creating. And if we want to hear the effect of the tremolo, just like the oscillators, we also have to start that effect because it contains its own internal low frequency oscillator. So we're going to start it inside mouse press just to be on the safe side. Let's go tremolo.start. So now you can hear the effect of the tremolo, right? It's kind of moving the sound up and down, changing the volume. So let's play with this. We could map, let's say we're going to go and change the tremolo's frequency. We'll set that value. Let's map our change counter. So we know the change goes between 0 and half of n, right? We talked about that because if they change every other one, right, change is going to add up. It's going to trigger half the time. And let's map that to a number between, I don't know, let's say we're going to go from 5 to 20 hertz. So when there is not a lot of change, we're going to have a kind of a slow tremolo, or even lower than 5, maybe like 3. And then when there's a lot of change, it's going to start to vibrate very quickly. So 20 hertz is like fairly fast. Let's hear what that sounds like. So arguably some pretty annoying sounds, but you know, it's interesting how what it does is it still allows us to experience the data in a way that isn't just purely visual. And it does follow the patterns in the data because we are taking the data, mapping it to these attributes of the sound. Now we can experience it differently. So we don't necessarily have to look at it, we can listen to it. And even better yet, sometimes we can combine the two, like we're doing now, where we can appreciate both the visual aspect and then just add another layer to the experience by adding sound to it. So this is really ripe for a lot of experimentation. So this week, if this is something you're interested in for the code exercise, you know, you could try to take you know, raw oscillators, adding some effects, and then mapping some of their parameters to data elements. Of course, you might want to use a different data set. For example, I would challenge you to revisit a previous example, a previous code exercise you did earlier this semester, where you had another data source and then try to map sound to it to see what happens. Okay? So this is not as much about creating, you know, the most beautiful sounds perhaps, or the most melodic sounds, but really trying to create more of a physical kind of gut reaction to the data by really having kind of a one-to-one mapping between elements of the sound, sound generation, and the data points that we have to work with. So we're going to leave it at that for this example. The other thing that we could try just for fun is I still have, because I've been remixing from previous examples, you know, I still have other files here. So we could compare, just for fun here, we could use a different file. Remember, how we're loading the file here is just using the binary, you know, load bytes function. So it could be an image, could be anything. Let's open this asset and use that instead and see if it looks or sounds any different. So this is the JPEG, right? And already it's got a bit of a different rhythm than our other file, just because its structures of 1 and 0s is completely different from the MP3. All right, so this could play for a while. These files have a lot of bits, have a lot of 1s and 0s in them, but something to experiment with as well, right? Remember to, you know, try different data sets and then see what comes out. Okay, so we'll leave it at that for this example. In the next example, we're going to switch it up, use a different data set, and talk about how you would create something maybe a little bit more melodic, and I will see you there.